Happy Monday, Trailblazers. This is Mr. Parrish. I'm not feeling so hot today, so that's why I'm not in the classroom. Trust me, I would rather be there with you guys than where I am right now. Let's go ahead and take a look at this question. You might recognize it from the tests from last Friday. We will give you your tests back tomorrow with your grades updated, so you will see exactly how it impacted your grade. My sense is that most of you did pretty well, but that's just a sense that I had by watching you guys take the test, so we'll see tomorrow for sure. I want you to write down most of this question. Obviously, don't write down the whole thing in your Bellinger, and then we will go through it question by question. If you would like to, you can quietly discuss with your partner. I'm going to give you, let's say, 3 minutes to look at each of these answer choices. And think about them carefully. This is like a very conceptual question where I want to push you guys on where to think about this one. So 3 minutes starting now. You guys have 1 more minute. Okay, I find this question really interesting because it is something that most people are witness in their regular life, and it is something that you really need to think about in terms of chemically speaking. It's just a really great question to test if students really understand what they're seeing. So I'm just going to evaluate each statement, and then we'll see which one makes the most sense. So we start with dad, where it says they are bubbles of heat, so the bubbles at the bottom are bubbles of heat. I could understand why you would think this would be the correct answer, but heat really isn't matter, right? So it wouldn't make sense that the heat would rise to the top because heat doesn't have a density. Heat is just energy, right? So the bubbles can't be heat because heat doesn't really take up space. It's just energy. It's not matter. Okay, let's take a look at Grandma. Grandma says the bubbles are filled with air, which I could understand also if you pick that one. But my question to you would be, how did the airs get to the bottom of the kettle? if it was full of air, or if the bubbles are filled with air, like how can they start at the bottom of the kettle? So it can't be grandma either, because the air has no way to get to the bottom of the kettle. Carlos, they are an invisible form of water. So this one we'll talk about in a minute. Mom, the bubbles are empty. There is nothing inside them. That's not the case either. Bubbles must have something inside them in order to maintain their structure. And then last one, Victoria, the bubbles contain oxygen and hydrogen that are separated from the water. I don't know what the data is from this year, but in the past 2 years, Carlos and Victoria are the most popular answers. Victoria is usually the more popular answer. And the reason most students give me, and I want you to raise your hand if you picked it for this reason, is because it sounds smart. Probably like 10 people raised their hand. So it's not, just because something sounds smart does not mean it's the right answer. If you think about it, if the bubbles contained hydrogen and oxygen that are separated, that would be a big problem, because most kettles are really close to open fire. And what do we know about oxygen and hydrogen? They're both combustible. And so I'm pretty sure you guys have all seen a tea kettle just boiling on your stove before. You probably haven't seen it blow up because of the oxygen and hydrogen that's coming out of there. So the water particles don't split into oxygen and hydrogen. So that's why Victoria is wrong. So obviously that leaves Carlos. They are an invisible form of water. What's actually happening is that steam is produced, right? That's the invisible form of water. And so the liquid water at the bottom of the kettle changes to gas and then is expelled through the top of the kettle there. So in this situation, only Carlos was the one that made the most sense. And that's another hard thing about this question, is that Carlos isn't right. Like, what he says it's not exactly right, but it is the one that provides the best explanation. If you would like to follow up with me about this, we can talk about it when I return tomorrow. Okay, you should have all received a sheet when you walked in the door of the map of stoichiometry. This is what's always been on. This is what's been on the wall all year long. What we're going to do is we're going to fill it in, and you guys are going to use it today in class. Before we move forward, I just want to say that on Wednesday we are going to have a day of retakes. So if you're interested in retaking your grade, if you're someone who still needs to bring up their grade before the end of the school year, we will have a day in class to do that. But I am expecting you guys to work hard and to work diligently for who's ever in the room today. Go ahead and turn to page 15 in your packet. All you need is a calculator, a periodic table, and page 15 in your packet. I'll go ahead and give you 1 minute to take that out. Okay, I think that's enough time. So now we're looking at our molar roadmap here. So you're going to have your own version of this now sitting in front of you, so if you need to use it for anything, you can. So the first thing we're going to fill in is the triangles at the top. So this is our particles, molecules, formula units, and atoms. You can, of course, abbreviate formula units to FUN, so you don't have to write it each time. And anytime we go from molecules, formula units, to atoms to moles, we have to use Avogadro's number, which is 6.02 times 10 to the 23. So that is our bridge to moles. So anytime you're going from molecules to something else, you need to be using this number. The next thing we're going to fill in is mass, right? So that's anytime we are given grams. And if you go from mass to moles, or moles to mass, you need to use the periodic table where you have to find the molar mass. All right, the next thing is for volume. Anytime you go from volume to moles or moles to volume, you're going to use 22.4 liters. And then the last part is for moles to moles. You're supposed to use the coefficient from the balanced reaction. Okay, so we've talked about each of this before, especially on the left side. We did it in our old unit on dimensional analysis. But now we have a mirror image on the right side as well, where we're going to use the same bridges to sort of go back and forth. And so this roadmap is really useful because it allows us to really chart our path for each of the calculations we are going to perform. Today, the longest calculation you should perform should be 3 steps. So it could be from volume to moles to volume, or volume to moles to molecules, or volume to moles to mass. Once you have moles of a substance, you can really find whatever desired particle that you need. Every calculation you do today should have moles to moles at the very least. Maybe it's just one step, moles to moles, but it should have at least that mole to mole step. Alright, so go ahead and take a look at page 15. We're going to start with mild problem number 1. On the mild problem set, you get the balanced reaction already done for you, so all you really have to focus on is the calculation. And so if I read the question, it says, if 7 moles of nitrogen react, how many liters of ammonia gas will be produced at STP? So I have my nitrogen here on the reactant side, and then I have my ammonia here on the product side. So they're asking me if I have 7 moles of this, how many liters of ammonia gas will be produced? So I'm going to start by sort of charting out my plan, and they give me moles. So I'm going to start here where it says given moles. And then I want to find liters of ammonia gas. But if you look back, I can't go from moles to liters right away. I have to go to wanted moles first. So I'm going from given moles to wanted moles, and then finally to given liters down, or wanted liters down here. So it's going to be a 2-step calculation. So if I look back here, I'm going from moles to liters, and I like doing this because it really reminds me what should go on the top of each of my fractions in the calculation. So I'm going to start by writing my 7 moles of nitrogen. I'm going to multiply by a fraction. Whatever my unit is here, in this case moles of nitrogen, I'm going to put that on the bottom. And then I look up here, I'm going from moles to moles, so I'm going to put moles of NH3 on the top. And at this point, when you have moles over moles, you're supposed to use the coefficients of the reaction. So the coefficient of nitrogen is 1, because there's nothing there. And the coefficient of ammonia is 2, because there's a 2 there in front. So it's 2 over 1. Now that I've done my molar conversion, I have to go to liters. So I'm going to put moles of ammonia on the bottom, and then liters of ammonia on the top. And if I just flash back to my chart here, when I go from wanted moles down to wanted liters, I'm supposed to use 22.4. So let's sort of catch up here. So I'm going to put 22.4 on the top, and then this is liters over moles. So anytime you have moles over liters, or grams over moles, or particles over moles, moles always gets a 1. So the only time moles doesn't get a 1 is if you have moles over moles here in the center. And you might be thinking, like, why does nitrogen get a 1? I thought you said if it's moles over moles, it doesn't get a 1. It can have a 1 as long as there's no coefficient in the front. So the coefficient of nitrogen happens to be a 1. That's why it gets a 1. Liters would always get moles as a 1. Okay, so if I type this into my calculator and multiply it across, I get 314 liters of ammonia. And if I check my significant figures, I have 1, 2, 3, and then in my final answer I have 1, 2, 3 as well, so that's my final answer. Okay, let's go ahead and turn to the Sizzlin problem, which is on page 18. So go ahead and flip to page 18. This is Sizzlin problem number 1. Alright, so it says, in a beaker, potassium reacts with magnesium bromide to produce potassium bromide and magnesium metal. And if 75 grams of magnesium bromide react, how many atoms of magnesium are produced? So I'm going to flash back real fast to our chart here. They give us grams, and then we're going to go to atoms. So if I look back at my chart, which you guys should have in front of you, they give me grams, which is the circle here on the left. And I'm going to go to atoms, which is the triangle up here on the top right. So I still follow the same general pattern. I go from mass to moles, that's my first fraction. And then moles to moles, that's my second fraction. And then now that I have moles of what I want, I can find anything that I want on the right side. In this case, they asked for atoms, so that's what I'm going to find. So I should have a 3-step calculation here. So let's sort of flashback here. Okay. The first thing I have to do before I start writing the fractions is writing the reaction. So the sizzling problems, you have to write and balance the reactions on your own. I'm going to give you guys a minute. Try to write this reaction. Okay, so for writing this reaction, they say potassium reacts with magnesium bromide. So that's going to be our reactants. Potassium is K, and magnesium bromide is MgBr2. Remember, this gets a 2 because it takes 2 bromides to cancel out a magnesium. It says to produce, so that's my arrow. And then I have potassium bromide. This is KBr because K is positive 1 and bromine is negative 1. And then magnesium metal is left by itself. Now to balance the reaction, I'm going to have to put a 2 in front of the KBr and then a 2 in front of the K. So remember, K and Mg are by themselves, so I'm not going to write their charges. They don't get any numbers down here because they're not one of the 7 diatomics. So I just write the metals when they're by themselves. Now that I have my balanced reaction, now I can perform my calculation. So I'm starting with I'm going to go from grams to moles, and then to moles, and then to atoms. So again, if you need to be reminded of our, oops, sorry, pressed the wrong button there. If you need to be reminded of the chart, we're starting at grams, and then going to moles, and then finally to atoms up here. So it's going to be 1 step, 2 steps, 3 steps. Press forward. Okay, so this is going to be the top of my fraction. This will be the top of my first fraction, should be moles. The top of my second fraction should also be moles. And then the top of my third fraction should be atoms. So I start with 75 grams of magnesium bromide. I draw my fraction bar, and I put grams of magnesium bromide on the bottom, because that's what I'm getting rid of. And then I need to go to moles, so I put moles of magnesium bromide on the top. This is grams over moles, so this is not the moles over moles thing, so that means moles should get a 1. And then for grams of magnesium, I need to figure out the molar mass. So bromide is about 80, and there's 2 of them, so that gives me 160. And then magnesium is 24.35, so then I add that one to the 160, and that's how I get 184.11 grams. So I should have used my periodic table to find these numbers here. Then I multiply by a fraction again. I take moles of magnesium bromide. I'm going to put that on the bottom. And then on the top, I'm going to put moles of magnesium, because that's what I want to find. That's my wanted substance. I could find potassium bromide, or I could find potassium, but since they asked me specifically in the question about magnesium metal, that's what I write on the top here. This is moles over moles, so I have to use the coefficient. The coefficient of magnesium is 1. The coefficient of magnesium bromide is 1. So I'm going to put 1 over 1. And those of you that like math, you're probably like, that really does nothing. You're right, it really does nothing. But in this situation, it allows us to get to moles of magnesium. Next, I'm going to take moles of magnesium, put that on the bottom. And then I want to find atoms of magnesium, so I put atoms of magnesium on the top. And in 1 mole of magnesium, there's 6.02 times 10 to the 23 atoms of magnesium. So now that I have my units set up, I just type these numbers into my calculator. And I get 2.4 times 10 to the 23 atoms of magnesium. I check my significant figures. I have 1, 2 for 75, and I have 1, 2 for 2.4 times 10 to the 23 atoms of magnesium. So this is what the sizzling problems look like. If you're looking for a challenge, these are the ones that you need to choose. For those of you that aren't looking for as big of a challenge, you can stick to the mild and the medium questions. All of the answers to this problem set are on page 18. So if you look at the bottom of page 18, they give you the answers for the problem set. So you can check to see whether you're doing it right or wrong. Yeah, so for the rest of class, I want you guys to choose some problems to work on. You should be able to complete 5 problems off of any page. You can choose mild, medium, hot, or sizzling, and you can mix it up if you like. And then you can check your answers on page 18. Again, I really apologize that I can't be there today. I'm just feeling a little bit under the weather. But I know you guys are going to do your work and get as much practice on this material as you can, so that when I come back tomorrow, I can sort of remediate and take a look at exactly what you guys need help on, or those of you that need to be pushed, I can push you in the right direction. I think that's it. I'm a little bit spacey right now because I'm not feeling too great, but I'm pretty sure that's all that I need to say about this. Please be respectful of who's ever in the room and follow their instructions. Alright guys, I'll see you tomorrow. Have a good day.